Chapter 9, Section 1, Inequalities and Applications. We're going to talk about solving inequalities and some of the applications that could involve inequalities. Now, what is an inequality? Well, we've talked about equations, and we've used equations and rules like the addition principle and multiplication principle to solve equations. We're going to look at this with things that are not equations. So instead of an equal sign that you have in an equation, we have one of these five symbols or representations of a comparison with these symbols here. And here's less than, greater than, less than or equal to, greater than or equal to, or not equal to. So here are some examples of inequalities. Negative 2 is less than a, or probably what we're used to seeing more often is to have the variable on the left side and x is greater than 4 in this case. Well, where did they get these symbols from to represent less than and greater than? I can kind of get the equal part here. They put like part of an equal sign underneath that to include an equality into that. And the not equal, I get that. But if I look at these, they have a lot of stuff we've started in grade school and stuff about trying to get kids to remember how these things work, like putting teeth on the less than symbol and tell them, that the alligator is going to eat the bigger one. Well, I think they got this symbol from a number line. If on a line, when we draw a line, we always put this arrow on the end. Well, this is the arrow part of that number line. And I could say this in a way and say, well, it's like negative 2 is left of everything that could be possible for this variable. Or in this case, for this one here, I could say all the things that are possible are to the right of 4 on a number line, and so on. Or all the values where x plus 3 ends up being left of or right on the number 6 on a number line, and so on. It's a very nice way to think about that, and I can get a visual image related to these inequalities, which might help eliminate some errors when it gets to this. Well, now they're going to show us that if we have inequalities, we need some ways to solve those. And what are solutions again? A solution is values for, like in these simple ones here, for x is greater than 4. Well, a solution for that would be like 5. If I put 5 in for x, 5 is greater than 4. That is a solution. It's not the only solution. In fact, there's an infinity of solutions just for this expression. I could put 6 in, 7, 8, 9, 10, 4 and a half, all these different values. So they bring up this idea of a set again. A set is a way to represent an infinity of things. So set notation is going to be used a lot in this deal because we're talking about non-constant or one or two constant solutions. So they talk about what a solution is. So we're looking for values in the inequality that will make it true. And then you can have a solution set, and when we have found those values, we say we have solved the inequality. Now, to solve inequalities, we can do some things like the addition principle. We've been doing this with equations. If I add one thing to one side, I can add the same thing to the other side, and I get an equivalent inequality in this case. In other words, what that means by equivalent again is that it has the same solutions as the original. So I don't change anything about what's going to happen for the solutions of this new inequality if I follow these rules. And they show it works for a is less than, or the less than symbol, and it works for the greater than symbol. And also says, hey, it'll work for less than or equal to, or greater than or equal to. Now the multiplication principle, there is one change. this first part here, they start talking about this c. C is the number we're going to multiply by. And if that is positive, it's exactly the same as what we do with equations. In this case, I end up with a is less than b. Well, I multiply c times both sides and I get ac is less than bc. Same with greater than. Then they have this section about negative numbers. Well, if I have a negative number that I multiply by, like I end up with this original inequality a is less than b, the equivalent inequality, if this c is negative, ends up reversing the inequality symbol. And the same for the other one. Now, a quick example I can just say verbally, and we'll probably look at a little bit later too with some of the examples, is if I have the inequality that 1 is less than 2, that's true, right? So I could write that down, 1 is less than 2. If I multiply both sides by the same number, right, that's a multiplication principle. If I multiplied 10 times both sides, I'd get 10 is less than 20. Well, that's still true. What if I multiplied by negative 10? I get 1 times negative 10 is negative 10 is less than negative 20. Is that true? Well, another way to say that would be negative 10 is left of negative 20 on a number line. No, that isn't true. I have to reverse the inequality symbol for when I multiply by negative. So what I'd end up with in this case, where I got 1 is less than 2, if I multiply by negative 10, I'd end up with negative 10 is greater than negative 20. So make sure this is a very important portion of solving inequalities. And here's an example that they go through solving in an algorithmic mode, which is a good idea to do in your work. And so I have this original 2x plus 4 is less than negative x plus 1. Well, the first thing they do is they add a negative 4 to both sides. They say subtract 4. I think you'll have more success and less errors if you stay in addition. But they're the same thing. Subtracting 4 and adding a negative 4 are the same thing. So they do it to both sides. They end up with this equivalent inequality, 2x less than negative x minus 3. Again, what does equivalent mean? That this inequality and this inequality, because I followed the rules properly, they have the same solutions. Okay? So then they decide to add x to both sides. Why? Well, because I have a negative x over here. That'll get that to go to 0. I do that addition. Now I have this another new inequality, and it's equivalent to these two prior ones. And hopefully always will be equivalent to the original. Make sure I don't make any errors. Well, to continue to solve this, they divide by 3. And they note this note here. The symbol, the less than symbol, stays the same since 3 is positive. Well, multiplication and division are related, right? In other words, I could say, instead of saying division by 3, I could say this and really write it this way. I don't have to write it a different way. What I've really done is multiply by 1/3. 1/3 times 3 is 1, and I get x, 1x. 1/3 times negative 3 is a negative 1. So I have a variable less than a constant. I have probably the easiest representation of all solutions for this inequality. Okay? So a very good method to do this is a set notation. Again, this is how this reads. This is a set of x such that, that little pipe symbol, such that x is less than negative 1. Now here's another way to represent this interval notation, is they put rounded brackets around this, and they say negative infinity, comma, negative 1. This means that it's everything left of negative 1 all the way to negative infinity. This works probably in graphing when we talk about this. Instead of using open dots, they use this curved parenthesis to represent that it's very close to that, but not including that value. Well, they go through and we could say, well, another way I could do this kind of problem is treat each side of the inequality as a function and graph that. And when I graph that, I end up with these two lines. And where their intersection is probably the most interesting part. Is I end up at this point of negative 1, 2. Well, when I'm looking for solutions for x, I'm looking for x values that will work, right? Now, if there was an equal sign there, it would actually be x equals negative 1. That's where they end up having the same values. So when it's less than, they go through a process of saying, well, what would happen if we put numbers in those functions and so on, and look at the ordered pairs. And here's kind of what I like, this representation of the solutions graphically on a number line. Hey, look at, there's a number line. What's that look like, right? That looks like the less than symbol. There's the greater than symbol, right? Well, if those two functions were equal to each other, like I said, is that when do they have a common solution is when x is negative 1. We end up with this ordered pair negative 1, 2. Well, we're talking about inequalities. In fact, this is the inequality that we'd have, which is 2x plus 4 less than negative x plus 1. Well, when we solve this, we end up with all the values that are less than negative 1, or x is less than negative 1. And graphically, this is how you could represent that. Okay? And if it was the other way around, it would be all values right of the negative 1 on a number line, or x is greater than negative 1. They go through this graphing, solving this graphically, and they're really trying to make an effort at saying, well, when these things happen, this point of intersection is important, and then I got to determine which side of the range, basically, like this is a representation of a range of solutions for both of these functions for that inequality, okay? Because we're looking for x values, that's a range thing, kind of going back to a prior chapter terminology, right? Well, I would probably never use that as a method to solve these kinds of things. So, but they're going to go through that. It's going to be a good lesson in graphing, those kinds of things. Here is the solution set expressed two different ways again. They find that the x is less than 2 right here, and they say x is the set of x such that x is less than or equal to 2. So in this case it could include the value 2. And notice in this interval marking now the difference is it doesn't have rounding. This square bracket next to the 2 means that it includes 2, and then everything left of 2 to negative infinity. Well, the last thing we're going to talk about is some of the applications here. The first one's talking about solid waste, which is not the most pleasant thing to think about and stuff like this. This might be some kind of author's attempt at humor to try to get a teacher to say some cuss words or something. So, but yeah, let's look at this problem. They start tracking the amount of municipal solid waste generated per person per day in the United States for several years. Now that'd be an interesting job. Although the data is not exactly linear, they basically created a linear function to represent a close transition of where this stuff goes. It would be kind of like taking this data right here and I make a coordinate plane, and here's my range, right? I start at year 2000, then I'd mark up the y-axis 4.72, and then in 2005 it's 4.67, 2007, and so on. I can mark all those points out with real data, and you're going to find that it possibly could follow a line, and that's where they get this approximation really of a linear representation of what's going on with this information that they're gathering. So they create this function where t is time in years, but it's years after the year 2000 because they didn't collect any data prior to year 2000. So, or they didn't initiate some kind of process to try to reduce the amount of human solid waste generated per person. So using an inequality, basically we can create something to represent what we think's going on with these questions that they're asking, because it is a good model. Okay, so this shows us some stuff. It really doesn't ask the question yet, and until it gets down here, it says is a good model. Here, M of T is the amount of municipal solid waste generated by the number of pounds per person per day. T is years after 2000. Using an inequality, determine those years for which less than 4 pounds of municipal solid waste will be generated per person per day. Boy, that's a mouthful. Okay. Well, strategies with word problems are always pretty similar. He says familiarize your stuff with the information. Notice that it starts in 2000 and we get these points. If I had this data I was looking at, these are really things that I can think about graphically by plotting ordered pairs and those kinds of things. And also they did this linear equation right up here for us. Then we translate that. If we asked to find the years for which less than 4 pounds of municipal solid waste will be generated per person per day, then we must have the result of this function needs to be less than 4. In other words, this expression which represents this function has to be less than or less than 4, right? So negative 0.3 t, t is years after the year 2000 plus 4.72 needs to be less than 4. So we have an inequality, we need to carry that out. So we solve that and we end up with this solution. Now notice that in this deal we had a negative 0.03 t is less than a negative 0.72. Well, what did they do, and all of a sudden they get this t is greater than 24? Well, they multiplied by a negative number or divided by a negative number to get this. Okay, so remember that the inequality needs to reverse. So t needs to be greater than 24. So what does that t mean again? It means years after the year 2000. So in 2024, would it work? No, it has to be greater than. So the next year in 2025, 25 years after that, right? It should work according to this inequality. And that's what they check. They put in 25 because it's greater than 24, and they test it. Yeah, it does work. We end up with 3.97 pounds of solid waste per person, and that is less than 4. And that's what they're trying to do, is find out when will this occur if we follow this model. So you state the answer really. Less than 4 pounds of municipal solid waste will be generated per person per day for the years after 2024. Okay, or years greater than 24 past the year 2000. You could say it a couple different ways. Now let's look at this next example. Job offers. After graduation, Jessica had 2 job offers in sales. Uptown Fashions, it gives a salary of $1,500 per month plus a commission of 4% of sales. Now Ergo Designs gives her a larger salary of $1,700 a month plus 6% of sales in excess of $10,000. Now I would assume she's going to probably try to find out which job will make her the most amount of money. And then they explain a couple things. If sales exceed $10,000 for what amount of sales upon Uptown Fashions, for the amount of sales upon would Uptown Fashions provide higher pay? Okay. Well, let's look at this thing. We need to organize our information and try to get a data and put it together so we can get some inequalities to solve, right? Suppose that Jessica sold a certain amount, say $12,000 in 1 month. Which plan would be better? Working for Uptown, where she'd earn $1,500 plus 4% of her sales, okay? Or 15%, or right here they figure it out. We'd end up with 1,500 times 4%. Percent means hundreds. How do I write that as a number? I could put 4 over 100 or 0.04. That's 100. That's all percent means, is hundreds. We do a lot of stuff with percents, but a fraction is a comparison, right? So all they're doing to try to get some familiarity with people to say use percents is to compare it to 100. So 4 out of 100 is what 4% means. Okay? Just to review there a little bit. So if I want to calculate that, I need a number, and that's 400s. Well, do your order of operations. I multiply 0.04 times 12,000, add 1,500 to it, I get 1980. Now what if she was working for Ergo Design Commissions and sold the same amount of money? And that's what they're doing here. Now in this formula for how they provide their salary or money for their employees, they paid only for sales in excess of $10,000. So Jessica would earn $1,700 salary plus 6% of everything over $12,000, or $12,000. Excuse me, I said over 12,000. I mean $10,000. And you do the math and you'd end up with 1820. So in this specific case here, where one thing happened, we could compare it to both situations and decide which one was which. Now, what if she sold a lot more, had a lot more money generated by sales? Could this Ergo Designs thing get to be more lucrative than the other one, right? So you need to understand it'll change, right? It'll hit an area where this Ergo Designs is going to be a better place to work. So they took one instance where they're going to sell, this person sells $12,000 worth of items, right? Well, since a similar calculation shows for sales of $30,000 a month, Ergo pays more. To determine all values for which Uptown pays more, we solve the inequality based on the above calculations. So let S be the amount of monthly sales in dollars and assume S is greater than 10,000 as stated above. We list the given information. Well, Uptown gives a salary of $1,500, 4% of sales, and so we could write this expression 1,500 plus 0.04s. Now Ergo Designs pays $1,700 salaries and 6% of sales over $10,000. Okay, so which is equal to 0.06 for the 6% times the sales S minus 100. Well, to get the whole salary, you'd have that 1,700 plus this commission formula, right? Well, what we want to know is when, in this case, and we could do this a couple different ways, but I could say when is Uptown, income from Uptown, going to be greater than income from Ergo? Okay? And that's how they write this inequality. They took these expressions, basically put an inequality, because we're not really saying when will it be exactly the same, and then if you only did that, you'd be going like, well, what happens if it gets bigger or smaller and stuff. This takes care of that. We're going to know a inequality that should tell us a situational stuff when saying, well, how much do you think you can sell? You could start plugging this into this and see if it, at that number, where would you be? So to carry out, we solved the inequality, which we generated, and remember you need to follow order of operations. Here I have a multiplication and addition. I can't do anything else here. I have a multiplication and a grouping symbol. Well, I look in the grouping symbol, I can't do anything with that S minus 10,000. That's as simple as it can get. Then I need to distribute this 0.06 over this binomial is what it is. So I take 0.06 times S and then 0.06 times 10,000. I get 600. So here's my inequality, and the next thing is they can combine like terms here. I can add 1,700 plus negative 600. They call it combining like terms, right? So I have this new inequality. They start solving this inequality by adding a negative 1,100 on both sides and doing that. So they get, in this case, they get 20,000 is greater than S, my salary. Or S needs to be less than 20,000. Now notice this is another area you got to watch out for inequalities. I just can't flip sides. You got to keep the relationship between these two sides. If I say the S goes, I want to put that over on the left side, I have to point or make sure that I still represent that the correct way. Well, you could check that by putting in something less than $20,000 and see what happens with your commissions. Okay. So the question then would be, if I was trying to figure out which one of these jobs I wanted to take, I would say, well, I need to know if I can make more or less than $20,000 worth of sales in a month. Because if I get that done, or I hit that criteria, it's going to make a decision about where I should be working. Anyhow, get to work on Chapter 9. Hope your tests went well, and I'll talk to you later.